Hi, my name is Jess Thorne. I'm a PhD student at the International Centre for Radio Astronomy Research, and today I'll talk to you about using the SED-fitting code Prospect to trace star formation over the last 8 billion years. Star formation in the universe has declined by an order of magnitude over the last 10 billion years. This means that galaxies are typically declining in star formation and transitioning from life to death as the universe evolves. This is most directly shown in the cosmic star formation history, which I show here from Medow and Dickinson 2014, where we see the global rate of star formation in the universe decline by an order of magnitude since redshift 2. So one of the most important questions in galaxy evolution science is what are the astrophysical processes that are causing galaxies to decline in star formation and ultimately die? So in order to do this, we need to look at galaxy processes and environment on large scales at intermediate redshifts where these galaxies are undergoing whatever is causing their death. So the reasons why this hasn't been done before is twofold. The first is that we need large complete samples of galaxies spanning a range of environments. So on this plot here, I show a series of different surveys where I show the median redshift of the survey on the x-axis and the fraction of galaxies observed or their completeness. So in the top left-hand corner, we have galaxy surveys like Gamma, SDSS, 2DF, GRS, which have low median redshifts, but very high completeness, allowing us to do group, pair, or environmental science. On the bottom right-hand corner, we have surveys like Z-Cosmos or Vipers, which have a much higher median redshift, but don't have the completeness required to do group pair science. This is where Devils comes in. So Devils will have a much higher median redshift and a much higher completeness. So Devils is the Deep Extragalactic Visible Legacy Survey. It's a spectroscopic redshift campaign using the Anglo-Australian telescope, and will measure the redshifts of 58,000 galaxies down to about WiMAG of 21.2. So the three fields we've chosen are Cosmos, XMM, LSS, and ECDFS. So we'll span a total of 6 square degrees. For the purposes of this talk, all of the work so far has been done in Cosmos due to the high completeness that already exists there. So once we have our large sample of galaxies, we need consistent measures of environment and galaxy properties over cosmic timescales. So the measures of environment for Devils are still yet to come as we're still observing, but for today, I'm going to talk about the galaxy properties. So the number one way we can measure galaxy properties is through their spectral energy distributions, or SEDs. So an SED of a galaxy is just a measure of the relative flux emitted by the galaxy as a function of wavelength. And the different shape of the SED is driven by the different processes that are occurring within the galaxy. So for example, the information that we are using in Devils comes from the far ultraviolet to the far infrared, where we see contributions from stellar populations from dust and potentially active galactic nuclei components. So SED-fitting is a technique that's been around for decades and essentially involves the combination of different templates or models together to model the entire emission of a galaxy. So these are things that relate to the stellar component, so your stellar templates or your star formation histories, your dust component, how it's attenuating, how it's re-emitting, and things like your initial mass function, AGN templates, how you want to model your metallicity, etc. And there are a number of codes that exist to do this, things like MagFizz or Segal, that basically combine all of the different templates together in different ways and essentially just rely on the same ones. For today's talk, I'm going to focus on Prospect, and the key benefits of Prospect is that it is entirely flexible how the user wants to define the star formation histories and the metallicity histories. So in Prospect, what we've been doing is using a skewed normal star formation history, where we can control the maximum star formation rate of our galaxy, where that peak happens, how broad the period of star formation is, and the skew of the particular galaxy. Does it ramp up quickly and decline slowly? The other thing we've been doing is allowing the metallicity in galaxies to grow or evolve over time. To do this, we've been using a simple linear mapping of metallicity growth to mass growth, i.e. as the galaxy forms more stars, it also forms more metals. To do this, we've implemented one free parameter, which just models the final gas phase metallicity of the galaxy. So this allows our galaxy to have stars within it of multiple different metallicities, but also to have galaxies with multiple different metallicities themselves. Recent work by Galspec et al. Has shown that by assuming something physical yet simple, we can recover the cosmic star formation of a history of galaxies. So this particular plot here shows what I showed before, the cosmic star formation history. So the Medow and Dickinson line is shown in black here, with various different assumptions about metallicity in the various colors. So by using a sample of 7,000 low redshift galaxies from Gamma and fitting them with Prospect and just altering their metallicity histories, we can recover a wealth of different cosmic star formation histories. So for example, the royal blue line represents fitting galaxies with a much lower metallicity than we'd expect them to have. And by doing this, we end up with a much, much older stellar population than we'd expect. Some of the common approaches are to fix the metallicity at solar, so 0.02, so that's shown in this orange line, where our peak is much too young compared to previous measurements. Or the other option is to allow the metallicity per each galaxy to be free, but it remains constant over the lifetime of the galaxy. And that's shown in red, where we wash out the peak and don't really have a peak at all. If we make a physical but simple approach, assuming something like closed box model for our metallicity, we can get a much closer cosmic star formation history to previous measurements. So that's shown in this black line here. So not only does the metallicity have a big impact on the cosmic star formation history, but it also has an impact on the individual star formation histories of galaxies. And by having an impact on the star formation histories, it also has a big impact on the stellar mass and star formation rates recovered. So we found that with our linear mapping of metallicity to mass growth, we've recovered older stellar populations than previous estimates. These older stellar populations have a higher mass to light ratio, which results in higher stellar masses systematically by 0.2 degs. And we found this at low redshift with gamma and at intermediate redshifts with devils. So on the left here, I show the differences in stellar mass between Cosmos 2015 catalog and the MagPhys catalog as a function of the prospect stellar masses. And you can see that in both cases, we're offset systematically at all masses by about 0.2 degs. On the right, I show the same, but for star formation rates, and you can see there is an offset, but we lie somewhere between Cosmos 2015 and MagPhys. So we need a large complete sample of galaxies. We have this in devils. Currently, the Cosmos field, we have redshifts combining spectroscopic, GRISM, and photometric redshifts for about 500,000 galaxies. And we have galaxy properties for all of these galaxies. We also have consistent measurements from prospect for the gamma sample, which means we can span low and intermediate redshifts with hundreds of thousands of galaxies. So once we have these large samples of galaxies, we can start to do some really cool science with it. And so one of the first things we've looked at is the star forming main sequence, which is the relationship between stellar mass and star formation rate of galaxies. So Davis et al. 2016 used a sample of low redshift gamma galaxies and found a very tight linear relationship between stellar mass and star formation rate. But other work has found in the Cosmos field evidence of bending, so a non-linear relationship between stellar mass and star formation rate at higher redshifts. This was found by Lee et al. In 2015 and Leslie et al. In 2020. So why do some surveys find linear relationships and others find bending? So what we did was we combined our consistently measured devils galaxies and gamma galaxies at various redshifts. So this one here is at about redshift 0.3. I show the devils population in blue and the gamma population in purple with our best fit main sequence in black. You can see that there is evidence of bending of the main sequence. But if we were to look at devils on its own or gamma on its own, you would see no evidence of bending. So it's only when we combine the two surveys together that we do see that evidence. As we move up in redshift, we lose gamma as we don't have the redshifts for the objects out there, but we still see the evidence of the bending in devils alone. We also see a clear evidence of the evolution of the normalization, i.e. as we get further out in redshift, our star formation rates get higher for a given stellar mass. But when we start to get to much higher redshifts at about redshift 3 to 3.5, we don't see any evidence of bending at all. It becomes very linear. So here I show all of our redshift panels. I know it's a lot to take in all at once, but the two key things I want you to get out of this is one, we only see the bend at high masses when we combine gamma and devils together. If we looked at either one of those, there would be no evidence of bending. The second thing is that at high redshifts, we don't see any evidence of bending at all, suggesting that not only does the star forming main sequence evolve in normalization, but it also evolves in shape. We suspect that this could be the emergence of bulges across cosmic time, where the bulge components contribute to the stellar mass, but not the star formation rates for the galaxies. So in summary, there are two things I want you to take out of this. Firstly, that modeling metallicity evolution SED-fitting is vital. Without it, your cosmic star formation history doesn't match previous observations, and it can have a huge impact on your stellar masses and star formation rates. So if you're interested in the metallicity side of SED-fitting, have a look at these two papers here. The left one is our original results finding that metallicity can have a huge impact on the cosmic star formation history, and the right one is using the metallicities we get out of SED-fitting to explore the mass metallicity relationship. And the other thing is that the star forming main sequence evolves in normalization and shape when we combine gamma and devils together using consistently measured stellar masses and star formation rates. So I've left the QR code for that paper there as well. I'm happy for anyone to reach out with questions via Slack, Twitter, or email. Thank you very much for listening.